Every image is a new discovery, and each will give humanity a view of the universe that we've never seen before. Today represents an exciting new chapter in the exploration of our universe. This telescope is one of humanity's great engineering achievements. The deeper you look, the less you understand, should be the motto of our cosmology, especially in the presence of James Webb. The dawn of a new era in astronomy has begun as the world gets its first look at the full capabilities of the James Webb Space Telescope. In a mission more than 2 decades in the making, NASA launched the most expensive science probe ever built, a $10 billion telescope that will attempt to capture starlight from the first galaxies to be born in the fiery crucible of the Big Bang. Despite experiencing multiple delays, the Webb telescope has finally delivered the goods. However, the latest images captured by the Webb telescope are sending shockwaves through the scientific community as they call our entire understanding of galaxy formation into question. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe. Join us as we delve into Webb's newest images, hinting at another universe at the edge of the universe. The generally accepted understanding of the universe is this: about 14 billion years ago, the Big Bang happened. In its early seconds, the laws of physics as we understand them didn't apply. All that would eventually become matter burst forth in a matter of seconds. First particles like electrons and photons, and eventually neutrons and protons, the building blocks of our atoms. Early seeds of stars, planets, and galaxies expanded out from that momentous point in time and space. It spread in such a way that the universe became highly smooth. Smoothness on an enormous scale just means that things within the universe are relatively evenly distributed. That is, if you were to put a cube around one section of the universe, it wouldn't be much more dense than another randomly placed cube. On a smaller scale, like between galaxies or within a solar system, matter is lumpy and filled with clusters. Physicists theorized that shortly after the Big Bang, something called inflation occurred. Essentially, what was once a tiny packed-together universe expanded out rapidly in a fraction of a second and continues to expand today. Inflation is part of the current standard model of the universe called the lambda cold dark matter, LCDM model. In LCDM, the shape of the universe's trajectory looks, in some depictions, like a funnel. It's wide at the top, growing and spreading further out over time. That's one interpretation, but there are others that have arisen from the same bits of information that scientists can actually observe and measure in real life. That is observational astronomy. The real-life information is crucial if scientists are to use models to make actual predictions about the future of our cosmos. Theoretical astrophysics is all about educated guesses shaped by the few things we do know for certain. Something called the cosmic microwave background contributes a big part of that observable information. The cosmic microwave background is made up of traces of radiation left over from an early phase of the universe. Radio telescopes can pick it up and then translate the waves into a heat map image of sorts. This image actually shows us how the contents of the universe were distributed about 400,000 years after the Big Bang, the earliest observable snapshot of a universe devoid of stars, solar systems, and galaxies. Everything was closer together and almost uniform except for tiny fluctuations that became the matter-forming stars and galaxies. This image serves as evidence that the universe started packed together and has expanded to where it is today. We also know that the universe continues to expand and can even measure to some degree how fast it's doing so. The cosmic microwave background also serves to confirm that an earlier version of the universe was very hot and our era is much colder. One way to test this model is by looking at very distant galaxies, equivalent to looking back in time to the first few 100 million years after the tremendous clap that started it all. The cosmos was simpler then, its evolution easier to compare against predictions. Astronomers first tried to see the earliest structures of the universe using the Hubble telescope. In 1995, over 10 days, Hubble captured 342 exposures of an empty-looking patch of space in the Big Dipper. Astronomers were astonished by the abundance hiding in the inky dark. Hubble could see thousands of galaxies at different distances and stages of development stretching back to much earlier times than anyone expected. Hubble would go on to find some exceedingly distant galaxies. In 2016, astronomers found its most distant one, called GNZ11, a faint smudge that they dated to 400 million years after the Big Bang. That was surprisingly early for a galaxy, but it did not cast doubt on the LCDM model, in part because the galaxy is tiny with just 1% of the Milky Way's mass, and in part because it stood alone. When the James Webb Space Telescope came along, our story of the universe was thrown into disarray. NASA's $10 billion gamble, in full operation since summer 2022, has shown that galaxies formed much sooner after the Big Bang than scientists previously thought, and that some of them are unexpectedly large, absolutely brimming with stars. These findings have thrown the whole scientific community into a new reality in which their existing theories no longer apply. The earliest and most massive galaxies observed by James Webb stand to contradict the prevailing thinking in cosmology. That's because other researchers estimate that each galaxy is seen from between 350 to 500 million years after the Big Bang, but measures more than 10 billion times as massive as our Sun. One of the galaxies even appears to be more massive than the Milky Way, despite that our own galaxy had billions of more years to form and grow. That means if the masses are right, then we are in uncharted territory, which will require something very new about galaxy formation or a modification to cosmology. One of the most extreme possibilities is that the universe was expanding faster shortly after the Big Bang than we predict, which might require new forces and particles. We believe we understand how gas, atom-based matter, falls onto these early galaxies and how star formation feeds back and prevents future gas from falling in. There's a limit for how fast material can accrete onto these objects, and although certain physical conditions can lead to an object temporarily overcoming that limit, it shouldn't be sustainable over such long time scales. Indeed, we typically see a maximum of 10% of gas converted into stars. But for galaxies to form so fast at such a size, they would also need to be converting nearly 100% of their available gas into stars. So, while 100% conversion of gas into stars is technically right at the edge of what is theoretically possible, it would require something to be very different from what we expect. A lot of people immediately assert that all of standard cosmology might be wrong, and perhaps we should throw out the Big Bang as the explanation for the origin of our universe. They hypothesize new laws of physics, like a new early form of dark energy that existed early on, or new physical phenomena, like the universe being born with supermassive black holes, or new exotic forms of matter, like a novel long-lived particle that decays into normal matter at relatively late cosmic times. While many people believe that the explanation is perfectly absurd, that is not the case. Remember that even before the historical launch of James Webb, a number of problems arose with our current standard model of cosmology. For instance, one issue is the nature of dark matter. One of the fundamental issues with the LCDM model is the nature of dark matter itself. Dark matter has not been directly observed. Its existence is inferred from gravitational effects on visible matter and the cosmic microwave background. Despite extensive searches using various detection methods, including direct detection experiments and indirect astronomical observations, the particle or particles that constitute dark matter remain unidentified. Another issue is dark energy and the cosmological constant. The inclusion of a cosmological constant, lambda, to explain the accelerated expansion of the universe is another contentious point. Originally introduced by Einstein and later discarded, lambda was revived after observational evidence suggested an accelerating universe in the late 1990s. The challenge lies in reconciling the extremely small value of lambda predicted by quantum field theory with the observed energy density of dark energy, leading to what is known as the cosmological constant problem. Structure formation and simulations also present challenges. While the LCDM model successfully predicts the large-scale structure of the universe and the distribution of galaxies, discrepancies arise on smaller scales. Simulations of structure formation sometimes overpredict the number of small satellite galaxies around larger galaxies like the Milky Way. This missing satellite problem suggests that either our understanding of dark matter is incomplete or the simulations need additional refinement, such as including baryonic physics, ordinary matter more accurately. For the cusp versus core problem, another issue within the LCDM framework is the cusp versus core problem in the density profiles of dark matter halos. Simulations tend to predict a cuspy central density profile for dark matter halos, whereas observations of dwarf galaxies and other structures hint at a more core-like profile. This discrepancy raises questions about the effects of baryonic feedback processes, such as supernovae and black hole formation, on dark matter distribution, which are not fully understood or included in current simulations. The The tension in Hubble constant measurements is another challenge. Recent measurements of the Hubble constant, which describes the rate of expansion of the universe, have shown a persistent tension between values obtained from local measurements using objects like Cepheid variables and those inferred from the cosmic microwave background by the Planck satellite. This tension suggests potential shortcomings in our cosmological models, including LCDM, or the presence of systematic errors in measurements that are yet to be resolved. Beyond these specific challenges, the LCDM model also leaves unanswered some fundamental questions in cosmology. For instance, it does not explain the nature of inflation, the epoch of rapid expansion. The LCDM model, while robust in many respects, faces ongoing scrutiny and challenges from both observational data and theoretical inconsistencies. One of the profound mysteries in modern cosmology revolves around the nature of dark matter. This elusive substance, inferred from gravitational effects on visible matter and the cosmic microwave background, constitutes roughly 85% of the total matter in the universe. Despite decades of research and numerous experiments aimed at direct detection, the particle or particles that make up dark matter remain unidentified. The quest to understand dark matter is not just about solving a puzzle of fundamental physics. It also has profound implications for our understanding of galaxy formation and the large-scale structure of the cosmos. The discrepancy between simulated predictions and observational data on the distribution of dark matter halos, such as the cusp versus core problem, highlights the complexities involved. While simulations often predict cuspy halos at the center of galaxies, observations suggest a more spread-out core distribution, especially in smaller dwarf galaxies. Moreover, the missing satellite problem persists. Simulations tend to overpredict the number of small satellite galaxies around larger galaxies like the Milky Way. This discrepancy raises questions about the interplay between dark matter and baryonic matter, which includes ordinary matter like stars, gas, and dust. Understanding how baryonic physics influences the formation and evolution of dark matter structures is crucial for refining our cosmological models. Another significant challenge comes from the measurements of the Hubble constant, which describes the rate of expansion of the universe. Recent observations using different methods have yielded conflicting results. Local measurements using objects such as Cepheid variables suggest a higher value for the Hubble constant compared to values inferred from the cosmic microwave background by missions like the Planck satellite. This tension implies potential flaws in our current understanding of cosmological parameters or systematic errors in measurement techniques that require further investigation. In addition to these observational challenges, the theoretical framework of the LCDM model also faces questions. The inclusion of a cosmological constant, lambda, to explain the accelerated expansion of the universe introduces the cosmological constant problem. Quantum field theory predicts a vastly larger value for lambda than what observations suggest, prompting physicists to grapple with the discrepancy. This discrepancy underscores our incomplete understanding of dark energy, the hypothetical energy that drives the accelerated expansion of the universe. Furthermore, the LCDM model's success in predicting the large-scale structure of the universe contrasts with its limitations on smaller scales. Understanding galaxy formation and evolution requires a nuanced approach that integrates both dark matter dynamics and the intricate processes of star formation and feedback mechanisms. The James Webb Space Telescope, with its unprecedented sensitivity and resolution, promises to shed new light on these processes by capturing detailed observations of early galaxies and their star-forming regions. The launch of the James Webb Space Telescope marks a milestone in astronomical exploration. Building on the legacy of the Hubble Space Telescope, Webb's advanced capabilities allow astronomers to peer deeper into space and farther back in time than ever before. By studying the faint light from distant galaxies, Webb will unravel the mysteries of galaxy formation and evolution during the universe's infancy. Early observations from Webb have already challenged existing theories of galaxy formation. The discovery of massive, star-rich galaxies dating back to just a few 100 million years after the Big Bang suggests a much earlier onset of galaxy formation than previously thought. These findings raise fundamental questions about the conditions in the early universe and the processes that facilitated rapid star formation in these ancient galaxies. Moreover, Webb's observations provide crucial insights into the evolution of galaxies over cosmic time. By studying the diversity of galaxies at different epochs, astronomers can trace the evolution of their structures, compositions, and star-forming activities. These observations will help refine models of galaxy formation and inform our understanding of how galaxies like the Milky Way have evolved over billions of years. Beyond galaxy formation, Webb's observations also contribute to our understanding of the cosmic microwave background, CMB. By studying the faint afterglow of the Big Bang, astronomers can probe the early conditions of the universe and test predictions of inflationary models. The precise measurements of the CMB by Webb will provide critical data to constrain cosmological parameters and refine our understanding of the universe's origin and evolution. In conclusion, while the LCDM model has provided a solid framework for understanding the large-scale structure and evolution of the universe, ongoing observations and theoretical challenges compel scientists to refine and expand our cosmological theories. The launch of the James Webb Space Telescope represents a transformative moment in astronomy, offering unprecedented opportunities to explore the cosmos with unparalleled sensitivity and resolution. As Webb continues to unveil the hidden secrets of the universe, it promises to revolutionize our understanding of cosmic history and inspire new generations of astronomers to push the boundaries of human knowledge.